Okay, here's the question. Could somebody help me find the proper equations and solutions to this question? Please, thanks in advance. And so I guess it's a question about electric potential energy. Before I really start digging into this problem, let me just say I already looked at it a little bit to see if I could get to a solution, and at first it threw me for a loop, and I'll tell you where it threw me off when we get there. But the ultimate answer here was something I didn't immediately see because I haven't actually done this type of question in a few years now, since I took a class on electricity and magnetism. And so actually, I know this is going to sound horrible, but I found it kind of a little bit fun because it threw me off, and I was like, oh man, what am I doing here? And then all of a sudden I realized, oh, this is a solution. And it was kind of it was one of those moments that like, oh, this is really beautiful solution. So here's the question. Two identical point charges, each with a charge of 1.7, 10 to the minus 6 coulombs, sorry if that's a little bit hard to read, but that's what it says, are fixed at opposite corners of a square whose sides have a length of 0.62 meters. And by the way, this is the picture we're looking at. You have charge Q, and we have another charge Q0, and the lengths of the sides are L. Alright, so a test charge, again, Q naught has a charge minus 1.9, 10 to the minus 8 coulombs, with mass of 7 times 10 to the minus 8 kilograms. It's released starting from rest at one of the corners. So that's what this is showing right here. It's at the corner. At one of the corners of the square, as shown in the initial figure, all three charges are on a horizontal frictionless surface. So that just means we don't have to worry about friction, which is good, because that friction just makes all the calculations much more ugly. Part A asks us to find what is the magnitude of the resultant electrostatic force on the test charge Q0 due to the other two charges when Q0 is located at the corner of the square shown in the initial figure. You must draw a free body diagram for Q0 when it is at the corner of the square. Alright, so Q0, I would say first thing, let's draw the free body diagram. And it's not that complicated, really. I'll get to parts B and C, by the way, after this. I just want to get part A out of the way. So part A, and if I were to do this problem correctly, I should list out all my given information and all that. And that's always a very good step to do, by the way. List your given, list what you're supposed to find and all that. I'm just trying to, do this a little bit faster, so I'm going to skip that step, but technically that's the best way to do it. I want a free body diagram of charge Q0, so I'll put a little dot and I'll label it Q0. And if I want a free body diagram of this, literally the only thing on here is the charge itself and the forces on that charge. And there's going to be two forces. One force that points from Q0 to this charge Q. So if I go down here, that would be a force. I'm just going to call it F1, force 1. Call it whatever you want. And then there will also be a force straight downwards from Q0 down to the other charge Q, force 2. However, something is true here is that these are the same exact charges, Q0 and Q, which means these force 1 and force 2 are actually equal. So it would be perfectly acceptable to actually replace either one of these with the other one. So for instance, I could say F2 equals force 1. They're the same magnitude of force. They have different directions, but the magnitudes are the same. So this is actually so this is true down here, that F1 is equal to F2. And I believe, does it ask for the resultant? Yeah, it asks for the resultant. So these are going in different directions, and basically we have to add the forces, but of course vector addition, you're going to end up with a force in this direction. Now I put that all as dotted, so this is a force which would be the resultant of force 1 and force 2 in some other direction, which you actually know the direction of that resultant. It's 45 degrees. I'm not sure we ever really need to use that too much, but it is 45 degrees from either one of these forces, take your pick. And we know it's 45 because these forces have the same magnitude. Strictly speaking though, if you're really just supposed to give the free body diagram, then I'm going to step back here and erase some of this stuff. Oh, well, that's a lot to erase, but sure, why not? I'm going to erase all that stuff because this would be your free body diagram. It's just those two forces, and putting the resultant on there is kind of extra. The resultant is the thing that's actually going to determine which direction the charge moves in. But really, this is what your free body diagram should look like. Alright, so, and we also have to calculate the magnitude of the resultant force on the test charge Q0. So that is not too hard to do. First question is, well, how big of a force is force F1? So this is where I looked it up just to be sure I still remembered, and you have Coulomb's law, where the force due to two charges is equal to K, which is Coulomb's constant, it's down here, times Q1, Q2 over the distance between them squared. So, go back here. Force 1 is equal to K times, well, one of our charges is Q0, and the other charge that causes force 1 is actually going to be Q. And that's up here, charge Q and Q0. The distance between them when it's at this corner is L, so we'll just, the distance squared will be L squared. Okay, I just want to make sure it was asking at that corner, and it is. Alright, so this will get us F1, and I'm just going to calculate that right now. Going back over here, we know Coulomb's constant is equal to 9 times 10 to the power 9, and I'm going to leave the units off. It's Newton meter squared over Coulomb squared. I'm going to leave that off here so it doesn't get too ugly, but you can, of course, include your units in your calculation if you want to. That's perfectly fine. In fact, it's a good idea. 10 to the 9th, yeah. It's a good idea if you want to make sure you're not making a mistake along the way. Q0, we are told, has a charge of minus 1.9 times 10 to the minus 8. That's 1.9. 1.90 times 10 to the minus 8. And then Q has a charge of 1.70 times 10 to the minus 6. It doesn't matter. 10 to the minus 6. And I'm going to divide by L squared. L is 0.62 meters. And while I was doing that, by the way, I was making sure that my units are all in the correct forms. Coulombs, meters. Like if this had been in centimeters or stuff, I would have to convert that to meters. So you do want to be careful with your units again. And then I can calculate this. I'm not going to do that by hand. I know it has a negative sign to begin with, but hey. And I'll bring up my calculator here. So it's going to be 9 times 10 to the power 9 multiplied by 1.9 minus 1.9 times 10 to the power minus 8, and then 1.7 10 to the minus 6 times 10 to the power minus 6, and that will be divided by 0.62 squared. So 0.62 to the power 2. And when I work that out, I get minus 7.56. I'll add one extra decimal point, minus 7.562 10 to the power, or times 10 to the power minus 4. And this is a force. The unit should be in newtons. Just double checking. Okay, that looks good. So that's the magnitude of one of these forces. Our resultant, however, remember, is going to be the combination of those two. Let me just call the resultant force F, okay? F is going to equal the square root of F1 squared plus F2 squared. And that's because F1 and F2 are perpendicular to each other. They're on the sides of a square. So we can actually use essentially what boils down to the Pythagorean theorem here. Just to remind you, F1 and F2 are equal, so we've already got both of them. Oh, and the reason this has a negative sign on it for this force, the sign indicates the direction. So negative means an attractive force. Positive would be repulsive. So this and this charge and this charge are being attracted. That's what this is saying. Okay, so what I did there is I just said these are the same, so I combined them to get 2F1 squared. And then I can get, if I want to do it, I can say square root 2 times F1. Literally, the square root and the square will cancel out. So I get square root of 2 times negative 7.562. You could leave the negative off if you want, it doesn't matter. Times 10 to the minus 4. F will equal then, so all I need is my previous answer times the square root of 2. And that is equal to negative, well, yeah, we'll stick with that, 1.069 times 10 to the minus 3 newtons. Just want to make sure, 1, 2, 3. Yeah, sure, that's good. This is one of our answers for part A. Yeah, okay, that's one of our answers for part A. So we want to make sure it has the correct number of digits based on our given data. So this has 3 sig digs, this has 3, this has 3, so we shouldn't have more than 3. So the final answer I'd give, and it does ask for magnitude, right? Magnitude, so get rid of that negative sign. It would be 1.07 if you round up, times 10 to the minus 3 newtons. And I'll put that in a nice little box so that we know that's one of our answers. Awesome. Now let's go to part B, where this question gets quite a bit more complicated. part B says, what will be the speed of the test charge Q0 when it reaches the center of the square, as shown in the final figure? Now let me explain to you what I tried to do with this when I initially did the question. I tried to figure out the speed, the velocity, based on the acceleration of the charge, which you can then, I would think, get from the force on the charge. Because I was thinking, well, this is the force, right? So the problem with that is you get a very complicated situation where the charge goes from here to the center of the square, and the force is going to change because the distance between the two charges is changing. So based on this distance changes, that means the force changes, which means the acceleration changes, which means it's not so easy to get the velocity. You have a changing acceleration. And things get a lot more complicated when you don't have a constant acceleration. So that was, let's just say, at the very least, to solve it, and I never did solve it that way, you would have to integrate for sure. It would be ugly. And so when I finally got the solution, I was like, oh, this is so much better. Here's what you got to do. You do this problem in terms of energy. Not the force, but energy. So let me put part B here. We know that there is another formula for electric potential energy. The potential energy is equal to, again, Coulomb's constant times the two charges divided by the distance between them. So let me explain a little bit of the physics here. If you look at this as an energy problem, it's actually, I think it's kind of cool. So up here, when it's at the corner, presumably it's not moving. I'm not sure if the question actually states it's not moving, but it's a reasonable assumption, I think, that at this corner it has no initial velocity. So that means if you look at this as energy, it's all potential energy and no kinetic energy. By the time it gets to the center, as we'll see later in the question, it no longer has potential energy. If I were to look at the forces off of the center, there would actually be two forces in opposite directions going from the center, which means the resultant force would be 0, and so it has, if with no force, there's no potential energy. So potential energy here at the center is essentially 0, which means it's all kinetic energy. So what you're doing is you're taking all your potential energy and transforming into only kinetic energy. And if you were to carry it on, you get to the other corner, your kinetic would transform back into potential, and then it would be going, then it would start to go the other way. You get kinetic, potential, and you'd actually get it to oscillate about here, which is pretty, I thought that was pretty cool. So with that understanding, we can actually treat this as an energy problem. And let's just begin by calculating the potential energy of the charge when it's at this corner. So I'm going to call that initial potential energy U0. And it's going to be the sum of two individual potential energies, U1 and U2. Each of those will be K times Q times Q naught divided by L. So what I'm saying is you take your two charges and you divide by the distance in between them. But that's only for the first force. The other one is the same though. Because you're dealing with the same charges, the same distances, it's actually the same exact thing. So all you get is 2 times K. Q naught Q0 over L. This we could use to calculate our initial potential energy. But there's one more thing to consider here. So let me demonstrate that by first calculating the potential energy when the charge reaches the center of the square. Now, according to the formula we're given, we'll call that U final. Why not? Let me actually put zeros on here. So this is initial 1, initial 2. This will be final 1 plus final 2. Sorry, I know my writing's getting a bit sloppy here. It's just a bit hard to write on a tablet like this. So final, it will be K, the same charge as Q, Q0, but the distance will be different. At the center, the distance essentially from the charge to this charge, we have to work that out. And it's a triangle. In fact, it's a right triangle with side length L and then 2 other side lengths. So this is a doable problem. Like, if I were to put this over here just to isolate it, we have side length L, and I don't know what this side is. I'm just going to call it A. We want to know what A is. This side length is the same. Okay? So, and this is a right triangle. Here's the right angle. So we can just use something like the Pythagorean theorem. We know that L squared equals A squared plus A squared. And if we solve for A, so that's 2A squared, divide the 2 and take the square root. So A would equal 1/2 L squared under a square root. Right? You divide 2 and then you take the square root. Yeah, so it's just going to be L over square root 2. That's what the length of that side is. So we know the distance between the charges, distance between these charges is L over square root 2. When you square that, though, which we have to do, oh wait, no, this is the one, in this formula you don't square, never mind, so it's just L over square root 2. And then there's the other force, the potential energy from this force. It'll be exactly the same amount. So it'll just be K, Q, Q0 divided by L over square root 2. And you can just add those together, and what you'll get, let me see, I don't want to get the math wrong here. 2K, so it should be 2 over, oh no, see, I was going to make a mistake there, wasn't I? You would get 2 square root 2 times K, Q, Q0 over L. I guess that math sounds like it works. Yeah, okay, that's right. I'm just thinking about it, and our final potential energy is actually higher because potential energies, this is one of these weird physics things you have to know. In this case, the potential energy actually gets bigger as you get closer to something. It sounds a little backwards, but it works. So what I'm saying is basically there's more attraction between the charges when they're closer together. That makes sense, right? The closer you bring them, it's like magnets. Bring 2 magnets closer together, there's a higher force between them. There's more energy there. But what really will matter here is the difference. So one of these minus the other. We'll see that in just a moment. So what I was saying here is that if we consider the point at the center to be 0 potential energy, That's the point where there's no potential energy and only kinetic, because that's the point where you get as low of a potential energy as you can possibly get in this problem. Then what we need this is for this to essentially be our reference point. This is as low as it gets. So we'll just take the initial energy minus the final energy, and what that will do is it'll kind of give us what the usable potential energy is up here when it's at the corner. That's what I was trying to look for, the usable potential energy. So this will be 2 K Q Q0 over L minus 2 root 2 K Q Q0. I feel like I'm starting to lose my voice here a little bit. So I'm going to factor out 2 minus 2 root 2. It will be negative. It's not a big deal. Q0 over L. Alright, so at this point I'm just going to plug in. I don't want to simplify anymore. If I remember correctly, K is equal to 9 10 to the 9th. Yep. Q is equal to minus 1.9. Okay. Times 10 to the minus 8. Or that was Q0, but either way. And then 1.7, 10 to the minus 6th. I should actually be leaving all the correct number of digits here. Put it 0 on this one, just cause. Divided by L, which is 0.62. Squared. Oh, there you go, trying to make that mistake again. It's not squared in this case. This is potential energy, not force. Alright, let me stick this into a calculator. Just clear that. We'll get a fraction going. So it's a 9 times 10 to the power 9. Let me make that easier. 9, 10 to the power 9. There you go. And then minus 1.9, 10 to the power minus 8. Uh, 10 to the power minus 8 times 1.7, 10 to the amount minus 6. And that's divided by 0.62. I don't know why I remember 0.62, but not the other numbers. Whatever. So here you go. That's what you get. But that's not the whole thing. That's just the fractions. So then I have to multiply that by 2 minus 2 square root 2. Don't need that. But I do need that. Okay, so the answer is 3.884, 10 to the minus 4. To the minus 4. I really should try to write more clearly. And this will be in joules because this is energy. Alright. So it did end up being positive, by the way, because of the negative sign in here. So that was nice. Either way, I was going to turn it into a positive quantity because we're concerned with the difference between the two energies, not the sign on the energy, because energy, you don't get negative energies per se, you know, except for, yeah, you really don't. You don't get negative energies, just think of it that way. Or you don't get negative energy differences, that's what I'm trying to say. Alright, so this is the the potential energy we're concerned in. Now, here's the final resolution to this. That's the potential energy at this point, as long as we consider the point in the center to be 0. So it has this amount at the corner and 0 at the center. Your kinetic energy will be, basically you take all your potential energy here and convert it to kinetic energy. So that means the final kinetic energy equals let's just call this some like delta U. The final kinetic energy equals delta U, the change in the kinetic energy. So kinetic energy is 1/2 mv squared, V final in this case. Remember, we're trying to find V, so that was the whole point of this. And I already calculated this, so I'll just have a number 3.884 times 10 to the minus 4. All we got to do now is plug in the mass and solve for velocity. So I want to multiply by 2, divide by the mass, and take a square root. So velocity final will equal 2 times 3.884, 10 to the minus 4, divide by mass, put the whole thing under a square root. And let's go ahead, work that out. So 2 times 3.884, 10 to the minus 4. I don't know what I was trying to write there, but there's nothing there. The mass, we're actually given that. It's 7 times 10 to the minus 8 kilograms. So 7.00, 10 to the minus 8. And kilograms are the basic unit in physics, at least, so we don't have to worry about that. The units are already in the right form, is what I mean. And that's it. We just do the math, try to figure out what all my scribbles mean, and we should be able to get the final velocity. So I'll put a square root and then a fraction under that. No, not that fraction. It'll be 2 times my previous answer. And yes, I know, I have a nice calculator. Sorry if you have to struggle with a less nice calculator. Took me a long time to get enough money to buy this one, though. Oh man, took me years. So that should be all correct. Yep. 105.346. So 105 point, we'll make it 34 meters per second, because that's the speed. Alright, so and I'll round that off. All of our initial values were 3 decimal places, so let me round this. This starts with a 1 though, so I'm going to round it off to 4 decimal places. You might use a different method of rounding than I do. That's fine. Whatever you're supposed to use, just use it. And that is the final speed when it reaches the center. There you go. Pretty nifty way of doing it, if you ask me. Let's just say, I mean, that wasn't exactly short, but that was a whole lot shorter than trying to find an integral or something like that. Okay. So that should be part B answered. Part C, what will be the amplitude of the resultant electrostatic force on the test charge due to the other 2 charges at the instant it arrives at the center of the square? This last part is pretty much just supposed to be a giveaway. If you got this far in the question, like you got past part B, then this shouldn't be that hard, really. All you got to do is realize when it's in the center, the two forces are of the same magnitude, but in opposite directions. So even though we're not asked to do it, I'll make a free body diagram. Why not? Charge Q naught. There's going to be a force this direction and a force this direction. And we can call them F1 and F2 again. Why not? They're not the same as the previous forces, so maybe you call this final 1, final 2, whatever you want to do. But they're actually equal. They're equal because, again, going back to this formula for the force, you still have the same charges. Coulomb's constant never changes. And the distance, in each case, we already calculated actually, is L over root 2, going either direction. So it's exactly the same force, but they're in opposite directions. So you could say the sum of the forces is 0. And that's the resultant. 0 is the resultant force, which is what's asked for, the magnitude of the resultant electrostatic force. So maybe, I don't know, just to be clear, F R for resultant is equal to 0 newtons. And that's just, you know, trying to verify that you understand that they're opposite direction. In this case, they completely cancel. I mean, just to give you a little perspective here, initially they didn't cancel because the two forces were 90 degrees apart, which means you actually get a resultant that points towards the center of the square. But once you get to the center, there's actually no force. And I believe that's it. If I missed something, feel free to leave a comment on the video and I will be happy to address it. But this was an interesting question. Not the shortest questions, but there you go. Hope that helps.